Indeed, I'm organizer, so maybe I should. Okay, so the next talk is Nafiz, and he will tell us about the Bethe correspondence for superspin chains from string theory.
Thank you. I would like to thank the organizers for inviting me to this wonderful conference, a wonderful place. Also, this is my first Blackboard talk since the start of the pandemic, so I may be a bit rusty. So this is another physics talk, and this is a collaborative work with Farooq Musavian, Surya Raghavendran, and Junia Yagi, and hopefully it should be on archive as well.
Yeah, so your collaborators online and monitoring. What you say? What you say?
Okay, so Farooq is in the audience. Let me first place the talk in the landscape of integrability that Masaito drew on Monday. So there were, by integrability, I mean the R-Matrices stuff. And there were at least 3 facets. So one of them was gauge theory. And so by gauge theory, it was implied that the gauge theory means essentially 4 region samples. There was also a geometric aspect. And there were various other things. But I will only have to say something about essentially the gauge theory side and some relations to the geometric side. I will have nothing to say about the other areas of integrability. The most direct thing in physics that relates to integrability is an integrable spin chain. Which essentially consists of a bunch of points carrying some representations of some group, and there's some Youngian acting on the tensor product of these things, which has a large commuting subalgebra that give you conserved charges. One of them is Hamiltonian, which governs the time evolution of the states in the Hilbert space. I will say a little bit more about it. Okay, so this is the physical aspect of integrability. So the physical aspect of the gauge theory here, it was 4 region Simons theory, where the analogous picture is that you have line operators labeled by various representations. And there are some gluons flying around. So if you start with some state in the tensor product vector space, it will evolve to some state, and that gives you the dynamics coming from the Hamiltonian. So 4-dimensional Simons is, of course, a quantum field theory in 4-dimensional spacetime, which I will take to be R2 times some. So here, this can be the complex plane or the punctured plane or some elliptic curve. The line operators here, they are parallel to the topological plane, which is this R2, and they have fixed locations in the complex plane. So the polymorphic direction will have punctures corresponding to the line operator and the locations of the line operators. So here, these representations will also carry some complex number, which in physics language are called inhomogeneities, but they're, so for example, for if this is the Young for G elements, those would be the evaluation parameters. And these would be the evaluation models. The analogs of these complex numbers here are the locations of the line operators in the homomorphic direction. Now, the physics version of the geometric picture. So these are some quiver gauge theories. They are defined by some quiver. The quiver is determined by the choice of Lie algebra here. So from the quiver, you can construct a geometric space, which is a quiver variety. And so that arises as the certain modulus space of vacua in the gauge theory, called the Higgs branch. And from that, so you can construct the equivariant cohomology with respect to some group actions. The group actions will be, so the group will involve the maximal torus of some group, which is the flavor symmetry group, and a certain U1 action, also a flavor symmetry. The idea is that this equivalent cohomology is the same as the Hilbert space that we would have here. Not exactly true, but almost. I will be more precise about that later. Okay, so this picture also involves gauge theories, but not for region cycles. Now, there is a quite remarkable correspondence called the Bethe gauge correspondence. It was originally proposed by Nafiz and Ishtiaque for GLM spin chain. So there were some restrictions about walking. What was it?
You can walk.
Oh. So what they found out is that given a Youngian, so given the Youngian of GLM and the representations, you can figure out what this quiver has to be. So here, for example, there's some other data as well. For example, the choice of an R-matrix, which can be rational, trigonometric, or elliptic. And these two choices correspond to the choices of these holomorphic curves, C star, or elliptic curve. So here we also have the choice. So these gauge theories defined by the quivers, they can be 2D, 3D, or 4D. So I will only focus on the rational part.
So is it true that that corresponds to changing cohomology theory to T theory or something?
I'm not sure about the 3D and 4D picture actually.
Okay.
Not sure.
That's true.
Hello.
Was there any question?
You have to unmute your mic.
Maybe he doesn't have anything.
Maybe mistake.
Thank you.
Okay, never mind.
Go ahead. Okay, so Nafiz and Ishtiaque gave a prescription for how to construct a quiver for the 2D gauge theories given the Lie algebra GLM and the representation. But this is more an operational approach, that there's some way to compute that thing. A conceptual understanding of why this correspondence exists can be given via the 4D Chern-Simons, which is that, so the relation between the integrable spin chains and 4D Chern-Simons is something that we have talked about a little bit in this conference, and they're very closely related. I mean, so much so that we can essentially think of 4D Chern-Simons as equivalent to a spin chain. I mean, they're essentially the same thing. And now, so there's a way of going from here to here. And the way is to use string theory. So I will essentially talk about this part. And I will also focus on the algebra GLM/N. So the next reference others really talked about GLM, and I will talk about the supercase, the generalization of that to the supercase. But actually, so I should also say that this correspondence was also clarified by Microsoft for the supercase, that given a representation how to construct the quiver, but for finite dimensional representations. I will talk about GLMN and Verma modules. All right. So that's what I'm going to talk about. Now,
Does the quiver only depend on Y? Not the dimension vector, but the quiver, does it only depend on Y or?
Yes. Yes, so here's something interesting. So for example, GLMN doesn't have a fixed linking diagram. So depending on the choice of linking diagram, you will have different quivers.
Well, perhaps following up Sachin's question. So, I mean, one question which can possibly arise is to consider more generalized cohomology series.
Right.
For example, the one version in algebraic topology is that you start with the formal group row, for example, and then you can define the generalized cohomology series. So that's something you might imagine exists on the upper side, right? So,
That's right.
so it sounds like but I don't know the counterpart
Yeah.
down there in gauge series side.
I think there are some papers about what, for example, case theory and some other cohomologies mean in terms of gauge theory, but I'm not very familiar with them. But it is very interesting to learn a bit more.
Yeah, for the elliptic case, it's an elliptic curve, so it's very geometrical. So I'm sure you can incorporate it. But if you start with the more general cohomology series, it's less obvious to me. Yeah.
More general than this K2 and elliptic cohomology.
Right. There is a universal. Yeah, there is even a universal one. That's what Kiren and Lazard and other people done.
I will briefly mention the appearance of integrability in Fourier Chern-Simons. So this was talked about a little bit earlier. So I hope this will make sense. I'm not going to write down the action of Fourier Chern-Simons. We have already seen what it looks like. It's just essentially the action of Fourier Chern-Simons with a holomorphic volume form on the complex curve. I'm going to consider Fourier Chern-Simons on R2 times C. The R2 direction is topological. Now we can consider line operators. Well, the line operators are always going to be in the topological plane, and they will have fixed locations in the holomorphic direction. And they will be labeled by some representations of GLM/N. And since this is GL, all representations of GLM/M can be lifted to an evaluation module with some convex parameter as the evaluation parameter. And those convex parameters will correspond to locations of these line operators in the holomorphic direction. So R-matrix in this picture appears when we cross to line operators in the topological plane and compute the expectation values, given some. So we can provide some initial and final states. And this will compute a matrix element of the R matrix. If we don't specify something, it's just the R matrix. So by this bracket, I have an expectation value computed in the holomorphic Chern-Simons theory. Now, because the theory is topological on R2, we can freely move lines around without changing these expectation values or really changing anything observable. as long as they don't intersect in the holomorphic direction, that is, their locations are distinct in the holomorphic direction. So assuming that all these complex parameters are different, we have an equation like the following. Colors all kind of look the same. I hope you can distinguish. So here I'm just moving the white line from the right side of the intersection to the left side. And assuming that all these lines are located at different points in the holomorphic direction, there's never any intersection. So all movements are happening in the topological plane, and the theory is topologically invariant, giving us that whatever this diagram is computing is the same as whatever this diagram is computing. Now, so at each intersection, we have some R-matrix. And if you write down what this looks like in terms of products of R-matrices, that will be essentially the Young-Baxter equation. Okay. So a consequence of the Young-Baxter equation is the following. Suppose we have a sequence of line operators, say L line operators, representing a spin chain with L spin sites. So here my Hilbert space is going to be V1 tensor, V2 tensor, VL. Now I can introduce another line operator in some representation, maybe the fundamental representation usually. Let me call it L. And so this also has a fixed location in the holomorphic direction. So these locations are called spectral parameters. So this has some spectral parameter eta. And so let me also compactify R2, well, not compactify, but make one of the directions periodic so that R2 now looks like a cylinder. And these vertical Wilson lines are vertical, and the horizontal Wilson lines go around the cylinder. Now, if I have two such operators, with two different spectral parameters. So the consequence of the Young-Baxter equation is that I can commute the locations of these two operators in the topological plane in the vertical direction, and that will not change the expectation value of this diagram, meaning that these two operators, well, okay, so these operators act on the Hilbert space, so there's some endomorphism, and they commute for all values of the spectral parameters. So because of this property, I can expand these operators in the spectral parameters. This will be some infinite power series, and since they commute for all values of the spectral parameters, I get commuting charges at each order. That gives us a lot of commuting charges. And so these commuting charges generate a commuting subalgebra of the Youngian called the Bethe algebra. And so this is essentially the source of integrability. That we can find simultaneous eigenstates of these L operators. So these are also called transfer matrices. I should read it. Okay, so solving a spin chain essentially means that find simultaneous eigenstates of Bethe subalgebra. That is, of all the operators in the Bethe subalgebra, which are the commuting charges coming from the transfer matrices. Now, so what do these eigenstates look like? So each eigenstate will have certain number of excitations over the vacuum of the spin chain of certain types. Now, so what does it mean? I will start erasing. Let me for now give a brief example. Let's consider just the GL2 case, which is the simplest case. So here, and also consider that each of these representations are just fundamental representations. So they are two-dimensional. And I can choose a basis that I can denote by spin up or spin down. So then a vacuum of that spin chain will be, let's say, all spins down. Then there is only one type of excitations, meaning that I can only change the state at a site in one way, which is that I can change the down to an up. So if I have one up and everything else down, so this is an excitation where there's an excitation of type 1, which is the only type, and that's it. So I can have two of such things as well. Now, there can be linear combinations of all states with one spin up, such that they kind of model a spin wave, meaning we can think of these excitations moving with certain speed along the spin chain. So the momentums of that spin wave is a parameter called rapidity. So associated to each excitation will have some rapidity. And we can think of the wave functions of the spin chain as functions of rapidities. So solving this spectral problem essentially boils down to finding the momentum that we must assign to each type of excitations of a fixed number, such that they become eigenstates of the transfer matrices. Right. So now the statements of the Bethe gauge correspondence is the following: that the Bethe vector or the Bethe eigenstates in a fixed Magnum sector so the magnums are these spin wave things, and by fixed Magnum sectors, I mean there are a fixed number of excitations of certain types. I will be a bit more precise about that later. So they are in one-to-one correspondence with the vacua of a truly well. So if we are talking about so this 2D will have n equals 2, 2 supersymmetry if you're talking about the super case. And this will be a 4,4 supersymmetric gauge theory if you're talking about the non-super case. The supersymmetry will be softly broken by some mass term, but essentially it's a 4,4 theory. So this was already worked out by Nekrasov-Shardashvili, and also this one for finite dimensional representations. I will talk about this one for infinite dimensional representations. So let me now explain for detail what the Bethe side and the gauge side corresponds to. So here we have this page. So we have a bunch of points or line operators in 4 different Simon series labeled by Verma modules. Lambda 1 is the highest weight. By m lambda 1, I mean the Verma module with the highest weight lambda 1. So there are L sites. So the length of the spin chain is capital L. So each side also has an inhomogeneity parameter, or the location of the line operator in the holomorphic direction. Also the evaluation parameter, if I think of these as evaluation modules. And something called the twist parameter. I will explain the twist parameters later. So for now, let me not write it. So there's some Hilbert space, which is the tensor product of all these modules. A generic state in this tensor product will look something like this is the highest weight, which is the sum of all the highest weights. So these alpha r's, these are the single roots. And these are some non-negative integers. And these integers are referred to as the Magnum number because so they correspond to how many times I have acted with a lowering operator of a certain type. And these correspond to, in the simple examples, changing the downspin to the upspin. So if I have GLM/M, I have m plus n minus 1 lowering operators, I can apply each of them a certain number of times. So that fixed Magnum sector means we look at a certain weight space where we have some fixed Magnum numbers.
One major setup different from Nekrasov setup, like is that the infinite dimensional module and the finite dimensional module, and what kind of thing that changes the.
It will change the quiver.
I mean, what causes the difference, like compared to Nekrasov?
I mean, probably you can just start with whatever representation you want. So let's say that I start with some representation that are infinite dimensional. So then the problem that I'm trying to solve is what do the Bethe eigenstates in this representation corresponds to in terms of quiver gauge theories? And the answer is given by a quiver that's different from the quivers that you would consider if you're looking at finite dimensional representations.
So quiver is different.
Yes. So as I was saying, that when I excite some state over the ground state, I can give that state the momentum and it can go around the spin chain. So each type of excitation will come with certain momentum parameter, which we will call the rapidities. The symbol that I will use for rapidity is sigma. If I look at a magnosector given by these numbers, R denotes the type of excitations. So for GLM/n, this goes from 1 to m plus n minus 1. And A refers to, so I can have MR excitations of type R. So A counts all the excitations of a given type. So A will go from 1 to MR. Now, given this data, there's a way to find the momentum that we must assign to each type of excitations so that the spin waves that we create are Bethe eigenstates. And these momenta are found by solving the Bethe equations, which are pretty famous. So, I will write it down, but it doesn't look very nice, but actually it's fine. So the Bethe equations look like the following. I'll write the equation and then I'll explain what the terms are. Okay, so most of the symbols have already been introduced. ARS, it's the Cartan matrix, or the components of the matrix. H bar is Planck's constant. So I'm solving a quantum mechanical problem, so there's a Planck's constant. Okay, so there's this symbol. Which defines a grading on the set of integers from 1 to m plus n. If we want to talk about representations of Lie superalgebras, we have to choose a grading on the basis vectors of the fundamental representations. So we can define GL Mn as the endomorphism algebra of a super vector space. So we have to give some grading of the super vector space, and this is that grading. So M of these things will be mapped to 1, and the remaining will be mapped to 0. This is just some shortcut for a constant. So we solve this equation for, okay, so here, this is a variable that we're solving for. It looks pretty messy, but this equation has very nice analytic properties, and this can be solved in many clever ways. But now let me go to the gauge side and argue that the vacuum of the gauge theory corresponds to solutions of this equation. Well, I will essentially just state the gauge theory and not really prove that that is the case. And instead of trying to be very general, let me define the gauge theory in an example, and this will generalize easily. So I'm going to choose GL3/2 as my example. And so as I was saying that we also have to make a choice of the Kac-Dynkin diagram that defines the grading essentially, or the grading defines the Kac-Dynkin diagram. So for example, if we choose the grading 1, 0. So this set defines that grading that I was referring to. So this is a map from 1, 2, 3, 4, 5 to Z2, and these are the images 1, 1, 0, 0, 1, corresponding to 3 and 2. So this defines for me a Kac-Dynkin diagram that looks like this. So here a crossed circle represents a bosonic simple root, and a white circle represents a fermionic simple root. Well, the simple roots are essentially differences of the fundamental weights. So if two weights are have the same grading, then the difference is a bosonic root. If they have different grading, they have the simple root is odd. Okay, so this is my Kac-Dynkin diagram. And so let's choose a fixed magnum sector which has magnum numbers M1, M2, M3, and M4. Then the gauge theory, the two-dimensional gauge theory that we should be looking at is the following. The quiver is determined by the Kac-Dynkin diagram. The magnum numbers appear as ranks of gauge groups. So circular nodes in the quiver represent gauge groups for the gauge theory, and square nodes represent flavor symmetry. And the arrows represent chiral multiplets, or the matter content of the theory. So an arrow between M1 and L is a chiral multiplet in the bifundamental representation, which is so a map from M1 to L. Well, so this is a complex vector space of dimension M1. This is a complex vector space of dimension L. And these are maps from M1 to M1. So they are adjoint representations of UM1. So this is a real gauge theory, meaning that all these gauge groups and flavor groups are real. So the gauge group of the theory is UM1 times UM2 and so on.
My only bosonic node have adjoint chiral.
Perfect. So
I mean, my question is why?
Why?
Yeah.
So that will become clear when I explain the brain construction. If you're familiar with the construction of Hanani and Hori, you probably already know that we did parallel NSY brains to.
No, I'm not familiar.
Then I'll just- So this quiver already contains a lot of the spin chain data. So this has the fixed magna numbers that we should be looking at for the Bethe correspondence. This has the length of the spin chain in terms of the flavor groups. So these are UL flavor groups. And this also know about the Lie algebra in terms of the shape of the quiver. But some data are missing. For example, the highest weights. So these lambdas. And I missed one component in the Bethe equation. So let me write it down.
So you said before that the quiver is different from that of the Nekrasov susceptibility to in G1's in reply to G1's question. So what is the difference? For example, you take GLN case where there is a joint and
Right. So yeah. So first of all, that. And you have the quiver looks like this.
Okay.
So this is different type of quiver.
Okay, but then it doesn't have 4,4, I guess.
Which one? This one?
Sorry, the one on the right.
No, this does not. So for the super case, the symmetry is 2.2.
No, even when it's GLN, for example, even for the usual real algebra case, then I mean, at least one has 4,4 and the other doesn't, right? So
I mean, if I have this, does it have 4.4?
right. So yeah, if you have that, yes, that's what I'm asking. In that case, is it true that it still has 4,4?
I think so. I mean, the 4.4 symmetry is broken by giving masses to some of these adjoint multiples. So that's the only deformation that's happening.
Oh, okay, but that one is the arrow has a chiral orientation, right? So if it's 4,4, it's non-chiral. So whenever there's arrow, there should be an arrow in the opposite direction. So at least the one on the right.
I see you're referring to this.
Even if it's for the case of the Lie algebra GLN, it doesn't seem to have 4,4 supersymmetry.
I see.
Well, probably it's not important anyway, but I just observed.
Yeah, so for this picture, it's not important, but I wonder what I will have to change. We can talk about that. Sir?
Your representations are infinite dimensional. Is that the reason?
Sorry, which ones?
Your representations are infinite dimensional. Is that the reason? Even if it's non-super, your representation is still.
That's possible because that infinite dimensionality is related to having this chiral matter contact. But yeah, I will have to think about that.
I see. Can you see that one modular space contains the other? Like this final dimension was a truncation, right?
Yeah, yeah. So I'm
see
currently trying to see that, but I have not yet succeeded.
Okay. Yeah, it doesn't look obvious from this picture.
Yeah.
So the algebra being super Lie algebra causes this opens the possibility of infinite dimensional representation. Is that the
No, you can have infinite representations for bosonic.
Yeah, it's a separate issue. So yeah.
But there's some crucial difference between the Venn construction for this type of quivers and Venn construction on this type of quivers. So the component in the Bethe equation that I was missing is that there are some phases here. Well, not exactly phases, I mean, these are complex numbers, tau r. So we have one complex number for each single root. And so that corresponds to having a periodic spin chain. So since our spin chain is periodic, an excitation can go around the spin chain and come back. So because of that, we need to impose some kind of periodicity boundary condition. And so we can twist the periodicity by, so for each type of excitations, we can twist the periodicity by a certain phase. And that corresponds to these numbers tau r. So those numbers are also not obviously present in this picture, but so this quiver defines not necessarily a unique quantum field theory in the sense that the field theory has allows certain deformations. We can give masses to certain fields, and those deformation parameters will correspond to the missing parameters. For example, So we introduce masses for all the matter fields. So meaning that we give the flavor masses for all these flavor nodes. So I'm using very physics terminology. So if something is not clear, please ask, and I will be happy to talk about it. These are mu sub I L from 1 to L. This is for ULI. This is UL1. These are complex numbers. So these will be the masses for these matter multiples. And okay, so this one has a very important U1 flavor symmetry as well, in addition to these flavor symmetries. And under that U1 symmetry, the various matter fields are charged as follows. So the charges for these current multipliers are given by the entries in the Cartan matrix. So these are the diagonal entries where I have them, and these are the off diagonal entries. And charges for these are this is minus half A12, and that comes from the fact that there's a superpotential terms involving this loop, meaning there's a cubic term in the superpotential that involves composing these maps, and that has to have charge 0. So that determines the charges for these arrows. Let me briefly mention what the superpotential terms are. So they're these kind of loops whenever you can find them. These loops, this loop, and for the fermionic node, this one.
So that U1 symmetry is R symmetry?
It's a linear combination of two R symmetries, two vector R symmetries. So the superpotential terms will also give you the relations that you need to determine the Couper variety. We also introduce a mass for that U1 symmetry. Or U1 H bar. And this H bar will be the same H bar as the Planck's constant in the spin chain set. Now what we do is that we integrate out all massive fields. Then the theory that remains at the low energy is an abelian gauge theory. So you have the gauge group is broken to the maximal abelian subgroup simply because of these masses. So in the vector multiplexes of n equals 2,2 theory, there's always a scalar. And so we can write down this low energy theory in terms of that scalar field, well, a bunch of those scalar fields. And that actually will have some superpotential. Not superpotential, just some potential. And then we can minimize that potential to find the vacuum of the theory. So there will be some function, let's call it y, not the Yangian, just a y, which will be a function of all the scalars in the vector multiples. So here again, R goes from 1 to m plus n minus 1, A goes from, it depends on the Magnum numbers. And the vacuum equation is simply that you maximize this thing. Now, instead of setting this to 0, we should set this to 2 pi I z. The reason being that the potential is logarithmic. So it has some various branches and all of them are physical. So we should count all of them. So a simpler way of writing this is that you take the exponential and set it to 1. Now, the main idea behind the Bethe correspondence is that this equation turns out to be exactly the same as the Bethe equations. Some identifications are needed. So for example, I have introduced masses here, but in the spin chain side, I had the highest weights lambda. So they are related by non-trivial relations. There's no need to look at it very carefully. I just want to point out that the spectral parameters appear here, and as does the highest weight. The rest are constant. Also, another important thing is that, so we should think of h bar as something very small, because this will be a complex number. This is actually a location in the holomorphic direction when we think about the transforming side. So h bar is small relative to the spectral parameter. So if we plot these complex masses in the complex plane, we will see some clusters of points. So for example, if this is a Z1, so we will see a bunch of points found near this point, and those will correspond to the different components of the high speed for the first spin side. For the second spin side, again, near Z2, we will have a bunch of points, and their locations will correspond to these problem 2, the components of high speed.
Sorry, I forgot what is Z in gauge theory term.
Z.
Yeah. What is it?
So this itself doesn't have an independent meaning.
It doesn't have any meaning in 2D theory.
No, just for itself, no. But this combination has meaning as layer mass. And h bar has also meaning as the U1 h bar mass. So from there you can figure out, well, you can get information about the highest weight and Z simultaneously, but not independently. Okay, so that's the Bethe correspondence. Now, so the question is, why does this correspondence exist? If we just look at it, then the gauge theory looks an entirely different beast from the spin chain. So why do they have the same equations?
Did you say anything about the potential? Why? Or
No, I mean, you can compute it exactly.
okay.
It's a one loop exact computation. So we know exactly what it is, and if you compute it, take derivative, exponentiate, we will find the Bethe equations.
Okay.
So I looks like I will not have time to explain the band construction in much detail.
We obtain the same Bethe equations.
I'm sorry?
We obtain the same Bethe equations.
Yes.
That's this one.
Yeah.
So the sigma have different interpretations.
That's right. So yeah, the vector multiplier scalar from the gauge theory side corresponds to the replicated in the spin chain side. Okay, so why does the Bethe correspondence exist? The reason is that, so we can insert the Bethe side of the correspondence, the spin chain side, inside 4D Simon theory as line operators. And we can insert 4D Simon theory into string theory. So this is 4D Simons with gauge group GLM/N. And so we can insert this into string theory using a bunch of brains. And in string theory, we have dualities. And so what this dualities will do is that it will take the brain configuration for the 4D Simons picture and give you the brain configuration for the 2D quiver gauge theory picture. And the supersymmetric configurations of fundamental strings here, which corresponds to states in Hilbert space, become supersymmetric configuration of some D brains here, which correspond to vacui of the 2D theory. So if I don't get to explain the brains at all, this is the idea. So let me now try to explain the brains. Let's skip the questions.
What do you mean by the first arrow from Bethe to 4D Chern-Simons?
Oh, I mean, so here I have spin chains. And I mean that I can represent the spin chain in terms of line operators in 4D Chern-Simons.
Right, but the 4D Chern-Simons canonically gives the R matrix and things like that, which is related with the Bethe answers, but not exactly, right? So different things. So
well, so if you have an array of line operators, the evolution of, so if you have suppose you have a bunch of line operators labeled by some representation. The spectrum of the spin chain, the Hilbert space is really just the tensor product of these things.
yes.
Right?
Mhm.
I mean, the point is that this is a vector space on which there's a Youngian action.
Yes.
Now, the states in this Hilbert space comes from supersymmetric configurations of certain fundamental strings in a particular brane picture. And the point of this argument is that those fundamental strings will become certain D-branes after constructing for Chern-Simons in string theory and applying dual values. So
yeah, okay, maybe the one way to say this that if you restrict to the first arrow,
yes.
there is a Bethe answers equation, some concrete equation, the one you wrote on the left-hand side. And then what is the counterpart in 4D before going to string theory and branes and more fancy stuff?
So the counterpart here is that they give you a parameterization of states that will be simultaneous eigenstates of a Bethe algebra. I mean, so the tensor products of representations of line operators in 4D Chern-Simons has an action of the Youngian, or
Okay.
more specifically, an action of the Bethe algebra.
Okay.
So there is an eigenbasis for the Bethe subalgebra, right? And the statement of the Bethe correspondence is that the Bethe eigenstates correspond to a vacuum of 2D theory.
Okay.
So what we want to do here is to find a map from this Hilbert space into vacuum of some 2D theory.
Mhm. Okay.
So that's what I mean.
Mhm.
That I mean the Bethe eigenstates are already here,
Mhm. Okay.
and we want to map that to vacuum of 2D theories.
The string theory will provide a process to do this.
Yes, that's right. So I will not have one step. So let me just mention some key points. Well, so let me draw one brain picture and maybe that. So here we consider the following system. So I'm going to draw, well, I'm going to specify the brane configuration for the gauge theory. Okay, so let me make some brief comments if I can take 5 to 10 minutes longer.
Maybe 5. You have to go and get the
Right.
picture again.
Okay. So this is a 10-dimensional space, right? The part of it is R times S1, which is a cylinder. And there's a holomorphic direction C. So this part will be related to Fourier-Simons theory. There are some other real directions, and importantly, there are 4 real directions in which I turn on omega deformation. So what that means is that so there is a certain deformation in string theory or in quantum field theory, which reduces a d-dimensional theory to a d-minus 2-dimensional theory by looking at observables that are essentially fixed at the fixed points of rotation in a plane. So there are 2 planes where I fix things in terms of rotation, and everything that I'm going to observe are located at the fixed points of those rotations. So there are 2 types of NS5 brains that wrap this 4-dimensional space, and so one of them wraps one omega deformation plane and the other wraps the other omega deformation plane. There are some D4 brains that wrap the cylinder entirely, located at fixed position in the holomorphic direction. The positions are given by the masses of the matter multiplet. And these brains end on the NS5 brains. So in a certain direction, I will draw a picture, and they also wrap some omega deformation planes. And okay, some D2 brains as well. Let me quickly draw something. Okay, so roughly speaking, the vertical lines are the NS5 brains. The bold and non-bold lines are 2 types of NS5 brains, plus and minus. And D4 brains, D4 plus and D4 minus brains end on the NS5 brains, which is why they extend in a half line in one direction. And suspended between the NS5 brains, we have D2 brains. So this kind of brain configuration gives you n equals 2,2 quiver gauge theories. The reference is Hanani and Hori. Okay, so the vector corresponds to locations of the D2 brains where you can suspend them, and you still have something supersymmetric. So where does Fourier-Simons come in? So first we have to T-dualize this circle. So NS5s will remain NS5. D4 will become D3. And D2 will become D1. Then you S-dualize. So then NS5 will become D5 plus, D5 minus, D3 will remain D3, and D1 will become fundamental state. The picture will look exactly the same, except we now have D5 plus, D5 minus, D3 plus, D3 minus, and F1. Now, so one non-trivial thing is that this D5 brain theory, so there are some 60 n equals 1,1 super n theory on each stack of D5 plus and D5 minuses. One has gauge group UM, the other has UN. Now, one claim is that if you do the omega deformation, the 6-dimensional theory will reduce to 4-dimensional with gauge group GLM, and similarly for GLN. And if you have both of them, they are coupled by some matter that live at the intersection of D5 plus and D5 minus, and they provide some fermionic fields that combine with the gauge fields of the bosonic Fourier-Simons to give you a gauge field for the fermionic Chern-Simons, and you end up with Fourier-Simons with GLM/N gauge group. Another non-trivial claim is that these D3 brains, when located at certain positions, quantized to give a line operators in variable modules given by highest weights that are related by some equations that I had written earlier, but that relate. Okay, and supersymmetric configurations of fundamental streams provide you the states in the tensor product of all these evolution modules. And as the duality suggests, they are in one-to-one correspondence with supersymmetric configurations of D2 rings, which are solutions of this equation. So here, when we have fundamental strings, we have the Bethe equations for the spin chain side. And on the gauge theory side, we have this equation, and string theory relates both of them. So essentially, my work was based on this localization stuff, which I didn't get to explain much, but I suppose that's okay. That's too much physics anyway. So that's the end of the talk.
There are gonna be a lot of questions, but we're kind of out of time. So we're gonna have to get our presentation and you can ask Nafiz your questions.
Yeah, sorry for being a bit late. And so, as I was saying that I only know physics terms, so I used physics terms. But if any of you have any question, I'll be very happy to try to understand how that relates to more mathematical stuff.
Let's thank Nafiz again.